Good morning. Good morning, everybody, and welcome back. It's my pleasure to introduce our first speaker for today, Luc Jaulin. Luc is a professor at Bretagne in France, and he's a professor of control. He's interested in a wide range of cyber-physical topics, including and especially robotics and interval computation. I have the pleasure of reading several of Luc's papers, which I find very illuminating. So in addition to being very interesting subjects, he is really good at explaining things. And he has a very popular book on interval arithmetic that was also very helpful for me to come to learn about the subject. This is a rare thing to have somebody who's able to explain such advanced topics so well, and in addition to being very well recognized in the scientific community with things like the Raymond Moore Prize, which is offered to exceptional contributions to interval arithmetic. So without further ado, please welcome Luc.
Thank you, Walid. Thank you. So today I will speak about cyber-physical systems. So probably here what you can see, it is a robot. And first I would like to, before introducing cyber-physical system, maybe for us what is a robot? And what is a link with control? So in a robot you have two things. You have the mechanical part, and the mechanical part, in a mathematical point of view, it can be described by something like x dot equal f of x and u. U is the input, x is a state. So the state corresponds to the position of the robot, to the angle of the sails, to the angle of the rudder, and so on. The input corresponds to the control. So it corresponds to the rudder or to the tuning of this rope, okay, the main sheet. And to be a robot, so it is a mechanical system. To have a robot, we need a controller. So controller. A controller takes the state or some sensor, such as the GPS, which is here, the wind sensor, and so on, and will compute automatically U, the input of the controller. So this corresponds to the robot. So you have the brain and the mechanical system, okay, plus sensors and so on. Now I would like to explain that in Brest we work with ocean robots, mainly. And what I would like to show is what we mean by cyber-physical system. And in the context we are working with, I will present you a small video with a work we do with CGG to find gasoline at the bottom of the ocean. So this can be seen as autonomous robot. Everything should be autonomous at the end. So it's a project which is named Spice Rack with CGG. CGG, a company in France now. Okay. So you can see first, it is a robot. And we have many robots. Okay, here. So these robots can be seen as 1 pixel of a huge, huge sensor. So, okay. And all the mechanisms should work in a guaranteed way. So you will see that each robot will be put at the bottom of the ocean, like this one. It should be able to localize. We need to have a guarantee that it will be able to take it back, and so on. So it's important to have a reliable position of each robot at the bottom of the ocean. The localization system is mainly from the boat due to what we call a long baseline. So there is some with acoustic system. At this moment, you have some kind of explosion at the surface. The sound or the wave enter inside the bottom of the ocean, and the sensor collects some data. Okay. But they are not able to communicate with at the surface. The only way to communicate all data is to come back So they come back, and everything is inside their memory. We have to guarantee that the docking problem is solved. Then the big robot, which is autonomous, but it's not the same at the beginning. It's another boat. We have two boats. One which emit some robot, and the one which collect the robot. And after they change, all this system can be seen as an underwater cyber-physical system we are dealing with. And now, okay, whoop. So what we want to do here is to guarantee things. So it's on YouTube, this one. And what is, we have a state system. Assume that this system, as soon as it is controlled, there is no more input, it becomes something like a differential equation like this. So assume that I have a differential equation. Well, I will write here, I hope you can see. Sorry. So assume that I have a state equation like this. So we have a state x1, x2, and we have a box which corresponds to the initial value at time t equals 0 of the state. This is the kind of problem we want to deal with. This state equation corresponds to a cyber-physical system, if you want, autonomous, since there is no input. So at each point, x, we have f of x, which corresponds to the speed of x. Okay, so we have some kind of vector field, like this. Okay, so this is a geometrical view of what corresponds to a differential equation, a state equation. And then we want to know where the system can go and where the system cannot go. So we can understand that if I have a box like this, we need some method, guaranteed method, that are able to tell me that never the system will go here. So we can see some cones here. What does it mean? If I have a box like this one, I have several directions for the speed, for x dot. So this corresponds to a cone, I will represent like this, which is attached to this box. And for instance, this cone is attached to this box. So larger is the box, larger is the cone, of course. So we need some method that are able to tell me that the state here, there exists one state inside the box such that I can reach this point. Now, I need some method that tells me that here I am sure for all uncertainty I will never go here. So you have understood the problem. So I have a question as an exercise. Why here? So what is the yellow part? The yellow part corresponds to zone where I cannot decide if there exists a possibility to go here or not due to the precision of the algorithm. So I can decrease this yellow part and to make it thinner. Now my question is why here it's yellow? It means that I can guarantee that I cannot go here. I can guarantee that I cannot here, but here I cannot guarantee anything. So why? Do you have any suggestion? You have understood? No, it looks normal. So it's not possible to go here, from here, following the vector field. It's not possible to go here, but the algorithm cannot decide if we can go here or not. Yes?
So there might be discrete jumps in our system
No.
for our state?
No possibility to have a jump. Like this. Of course, in other kind, but here it's a simple system. Everything is continuous. Yes?
Something a spiral.
Yes, good. Good. It is what the classical van der Pol system. If I am here, I can reach this point, but I cannot reach this point. So there is some method. I will go slowly to this kind of method. First, to find the cone, we will need interval analysis, and we'll need some bisection algorithm to be able to compute such things. Okay, you have understood why we need some, and when I say guaranteed, it is not Monte Carlo method. For instance, a Monte Carlo method in this kind of context. You take many points inside here. You make a lot of simulation using a Runge-Kutta or any integration method, and you will be able to say, oh, I have a good idea that I will obtain this cycle, and I have a good feeling that I can go do here or here, but it is not a proof. What we want is mathematical proof. And the kind of tool that will be used in this context is very similar to what has used Warwick Tucker from Sweden to prove the conjecture of Lorentz, that the Lorentz system has a strange attractor. Okay, so I will have to present to start slowly and to start with interval analysis. So interval analysis, what is new with interval analysis? What interval analysis can do and that other methods cannot do, I can say like this. So a problem by Moore. Moore has solved this problem. You can do it when you want. I don't know. So I have a function f. This function is computable, so you can represent by an algorithm. And you have an input for this algorithm, f. And you have a box for x1, x2, x3, and so on. And you want to prove that for all x, the function will be positive. How can I do this? With Monte Carlo method, you take many points in x, all of them are positive, you conclude that probably the function is positive, but it is not a proof. Because maybe there exists one point such that the function is positive. So with interval analysis, we will be able to solve this problem, and it is considered as new. Before interval, it was not really possible. So okay. So if I have a function like this, I can answer with interval analysis, is it positive for all x1, x2 in this interval? So how it works, everything is based on set theory. So I give you some classical definition of set theory, the image of a set, the reciprocal image of a set. Probably you know this. So that's why I give you a small exercise. And just to start, I would like the answer for the first one. The image of A. A is a set with 5 elements. What is the image of F? Of F of A?
2, 3, 4.
Yes, 2, 3, 4. F minus of F of A.
Should be A.
No. A, B, C, E. Yeah? This one. The last one. B, C, A, B, C. Yes. Yeah, okay. So it's not exactly the same. So it's all what we need on set theory. Okay. Just okay, let's go. So if you have understood this, I will start with interval. What is an interval for us? This is an interval, so it's closed interval when brackets are closed. What is the image by this function of 2, 3? Four, 9. Yes, good. What is the reciprocal image of 4, 9? Minus 3, minus 2, union 2, 3. Okay. Okay, that's good. Now, interval arithmetic. How can I define? So we made a little bit of interval arithmetic. This is a formal definition, and I will try to explain on example what it means. So the idea of interval arithmetic, which was expressed by a formula before, let's say, for instance, this one. I take A inside this interval. I take B inside this interval. What about the product A times B? Minus what?
5.
5. And the maximum?
15.
15. Everybody agree? So, of course, minus 5 is possible because this time this is minus 5. This time this is minus 2. So what we do is we take all, and we take the maximum and the minimum, and we are sure that we enclose all possible values. Okay. What about this one? Okay, so I think you have understood. I give you the solution. Tell me if there is a problem with this. So this one corresponds probably to this one divided by this one. And I do not contain 0, but here 6 divided by 2 is 3. So I take all possibilities. And here I do not enclose 0. If I have minus 2 here, what should I get here? I will get the union of two intervals. But to apply interval analysis, so because if I have minus 2 here, I contain 0. So I will have two intervals. So what gives here the definition? A operator B. Okay, X, Y. I take all possibilities for the result of X operator Y when they are inside the interval, and I obtain a set. This set may be discontinuous. So in this case, I take the smallest interval which encloses this set. And it is how I define interval arithmetic operation. Okay, I want it to be closed. If I make the operation between two intervals, I still obtain an interval.
Sorry, I didn't get that. Okay. Maybe the next example.
Yeah, this one. Okay, what about this? So if I compute correctly, can I be as small as possible? Can I converge to minus infinity with this? Yes. Can I converge to plus infinity with this? So the set of possible value, all possible values for this. I start with minus infinity. I can reach all these values. I stop. Here it's not possible. And I can go up to infinity. What is this value? Probably minus 2 too. No? But to have this, I take the smallest interval which contains everybody, which will be minus infinity plus infinity.
So my question here is, how do you deal with 0 in this case? There is discontinuity at 0, and you don't...
So, no, I define, what is important is not to lose any value. I enclose all values, and I have an interval.
So to distinguish between open and closed intervals?
No,
Yeah.
all are closed.
All are closed, yeah.
So this one I represent like this, but I could represent like this. I could represent minus infinity plus infinity. I could say that it is R. Me here, I have written minus infinity plus infinity. Okay, I could have written this or this. Just a question of notation. But in fact, I do not contain minus infinity. But even if I open the bracket, it's still a closed interval because R is closed. R enclosed. It's not bounded, but it's not compact, but it is closed. Empty set is also considered as closed. Empty set is an interval. So if I intersect two intervals, I still contain an interval. So so I can define from the bounds interval operation. So for the multiplication, we said I take all possibilities. I take the minimum and the maximum. And from the bounds, I can implement some algorithm to compute multiplication, addition, division, and so on. So I do not explain how it is, but the principle can be extended to function, elementary function, trigonometric function, and so on. So it's the same principle. I take all possible values, and if the function is discontinuous, I may obtain here a disconnected set, in this case, I take the smallest interval which contains the set. So I can define like this. So just an example. What about this one? Remember set theory.
0, 2.
0, 2. No ambiguity. I take all possibilities. It is 0, 2. The smallest interval is 0, 2. What about this one?
It's empty set.
Empty set. So it is an interval. What about this one?
1, 7. Sorry, 0, 7.
0, 7. Okay, so I have to implement for everybody all these elementary functions. Okay, so what we use in Brest to deal with interval analysis and contractors and so on, I will define later, is IBEX or PyBEX, a Python version of IBEX, which I define interval, and I just an exercise, what it will print here. I don't know if you know Python, but even if you don't know Python, you will be able to understand what it should write here. So here it will write
0 square root 3.
0 and
Square root 3.
so
This is square, that's
square of 3 is
square. 9.
9. Okay, okay. What is?
Minus 10 plus 9.
So it will be something like minus 15 probably, and 10. Yes, yes, yes. What it will write here? No, I made a mistake here. So okay, square of sine. What it will write here? Forget this. Z is all real. So minus infinity plus infinity. Here it will write the square. So
Minus 1, 1.
square,
Oh, sorry. 1, 1.
0, 1, and so on. Okay. I hope that I'm right, yes. Okay, you have understood how it works. So boxes.
So SQR is square root or square? But you also have square. You can also compare it to it's also square.
Yes, excuse me, here, you take care, I made a mistake here.
So what's the SQR operation though? Is that square root or square?
Here it's square.
But the SQR function.
Square is square.
Oh,
So here it's chain, string.
okay.
So I write what I want, but okay.
Can I ask a question? Well, at the beginning, you showed this tripartition, what you can reach, what you cannot reach,
Yeah.
and the gray area. While here with interval, you just have 2. So,
What is important with intervals is to enclose all possible values.
that
So you may contain inconsistent value, but you should contain all possible values.
So in this case, the interval would include both the red part and the yellow part.
It will contain, yes, 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 as before, yes. Okay, so now I can define boxes. Boxes, or I will show you later a picture, but it is a Cartesian product of intervals. Okay, so it is a box. And it is a symmetric plane of the box. We have 3 symmetric planes. We'll see in algorithm when we'll bisect a box. It will mean most of the time we take the largest width, okay, or length, and we bisect perpendicular with respect to the largest sides of the box. Okay, we'll see later, but it is an image of a 3-dimensional box. So now, what is, in fact, interval analysis? It's a way to compute inclusion function. So it is a concept which is important is the concept of inclusion function. So I will try to explain now as this. I have a function here from Rn to, let's say, Rp. If I take a box like this, it is a box, the Cartesian product of two intervals, the image of a box by a nonlinear function is something which is like this. Let's say if it is continuous, it looks something like this. If the function is linear, the image by f, it's a polygon. What I want to compute, I want to compute a box which encloses all possible values. So how this can be done? It is what we call an inclusion function. If I enclose all possible values, I say that I have an inclusion function. We have the minimal one, which is here, the best one. This one is difficult to compute in general. But what we can do with interval analysis is to compute one easily. Okay. Now I want something more. If this box converges to a point, here we want to converge also to a point. It is also possible, and we'll try to show if I take nested box here with interval analysis, I will obtain also nested sets, of course, due to set theory, but also nested boxes as an output thanks to the inclusion function. So to understand this, we'll take an example as an exercise. Also, we'll have to do this exercise. I have a function like this. So it is a simple function, but it can be done for all type of function. I have a function with an expression. I know that x belongs to -3, 3. You will compute with interval analysis. I want you to compute the image of this interval via this function. So as an exercise, so you try to do it if you have paper. Everybody? I will do it probably here. Just to show that it is quite easy and general. So, x is equal to so normally, it is what you should obtain. Do you understand this? Now, what is important to understand, if I take this interval and if I contract it, you understand that this one will be contracted. And I will contract up to a point. Here, it will be contracted up to a point, this one. This one also. So the width of the interval will decrease up to 0. And at the end, I will obtain a point. It is what I say, it is convergent. It is monotonic, because when I contract this one, the result will be contracted. But it is convergent, because if I contract this one up to a point, here I will obtain a point. And it is what is represented in this picture. If I take a box, if I compute with intervals, I will obtain an enclosure, and I will converge to a point if here the nested box converges to a point. You have understood this? It's important to guarantee the convergence of the algorithms. Yes?
So you introduced two notions, monotonic and convergent.
Yes.
How do these relate? How do these two relate to each other? Is every monotonic, is every convergent monotonic in some sense, or?
No, no. I can imagine some function, inclusion function, that are non-monotonic and convergent, non-monotonic and convergent, but also some that are non-convergent and monotonic. But what I say is that I would like to say that for more, that if all operations are continuous, if the number of operations is finite, if everything is continuous, then I will be monotonic and convergent using this way. But I may have some better method, more efficient, more minimal, if you want, to compute inclusion function, but such as the centered form, and I will not explain here, that may not be monotonic. Okay, but here I try to stay simple, and if I use classical interval and arithmetic, I will obtain something which is convergent. Yes.
Here,
And
your x in x squared and also 2x, they should be the same x, the value of the
yes, 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 yes. So here it is not minimal. The minimal value is 328. So it is a dependency problem. When I compute with an interval, I am pessimistic because I have the value I consider here are independent from this one. It is called as a dependency problem or effect. But I still guaranteed. Okay, it's important to be guaranteed to enclose all values. Okay, so now just another example, function from R2 to R3, like this. I do this, and I will obtain here the minimal inclusion function. Minimal, why? Because you have a theorem from Moore that tells you that if for each coordinate function, 1, 2, 3, for each coordinate function, if the number of occurrence of x1 or x2 is never larger than 1, strictly larger than 1, then I will have the minimal inclusion function. Okay. So here it is minimal.
Could you re-explain what the purpose of the minimal inclusion function here is?
The minimal inclusion function, the best thing is to have the minimal inclusion function. You understand this? But what...
So, given your example before,
Yes.
you didn't have the minimal one because
No,
you didn't.
because x occurs once, occurs twice.
Right.
But here, x1 occurs 1, x2 1, 1, 0, 1, 1. So never more than 1. So I have the minimal inclusion function. I don't have the dependency problem.
This is just an example, or
Yes, it is an example.
I see it.
Or it's not always the case. Yes. Now, if I have an algorithm like this, for loops, and here I try to represent an algorithm, a simulator, what you want. Simulator of a superphysical system, something like this. When I have an algorithm, I take the same algorithm, but I do not implement it once more. I just replace the float, x1, x2, x3, by intervals. So I just have to download, to use overloading operator with the same algorithm, like this, but I change the input interval, the type of input. The same algorithm, I will obtain an inclusion function which is monotonic, which is non-minimal, so monotonic and convergent. Okay. You know now everything you should know on interval analysis. Now I will start with the algorithm. And what I want is not to compute with intervals, but to compute with sets. Because when we want to prove properties, we want to consider some uncertainties, not probabilistic uncertainty. When you have a number you don't know, for instance, the weight of a boat or the position of a robot, you will not represent by I still have 10 minutes here. That's good. That's good. Okay, I will represent by a set uncertainty. So it's what we call set inversion. No, so I will represent by a set, and I will explain now how to invert a set. So I will use the notion of subpaving a set, such that a set like this, which is represented in red, I can represent by boxes. I will now explain how we can obtain such a set via set inversion. So, excuse me, I will, so I have a set Y, and I want to compute the set of all reciprocal image of Y. So I will try now to explain how this can be done. Where is, yeah, hi, here, I will write here. I have a set, Y, it can be a box, and here I have a function f, x1, x2. I take a box. Here, the image of this box can be something complicated. For instance, this one. I can compute an inclusion function for this set. So this corresponds to A, for instance. This corresponds to f of A, easy to obtain using interval analysis. What I can say is that f of A does not intersect Y, such as here, then A is outside X, X which corresponds to the reciprocal image of Y. Okay? You understand this? If I take a box here, the image can be something complicated, but I can enclose it. So here it's B. If f of B is included in Y, then I can conclude that B is included in X. I am sure that here I am in the solution set. So using this, I have these two tests that makes me possible to decide if a box is inside the solution set or not. If I cannot decide, then I will bisect the box. For instance, if I take this box, the image will be like this. I'm not neither inside, neither outside, so I will bisect this box. And it is the algorithm, which is called CVIA, which corresponds to a set inversion problem. So I test if I am inside or outside. If I am not too small, I bisect, and I push in a list up to all the list becomes empty. And this is an example of, I wanted to show, yes, I still have a few minutes. I wanted to show here how it works in practice. So I open Vibes just to draw sets, to draw boxes. I will use here Python, so spider. So it will open spider. Up. I call here, so don't look at the program first. I define my function and so on, and if I run it, I obtain here a solution of the set inversion problem. And if I zoom, so the solution is, you can see the yellow boxes. So red means inside, blue means outside, and yellow means I don't know. You have a proof that for all you are inside, for all you are outside. It is a set inversion algorithm. If this corresponds to the size epsilon, if I'm not satisfied by the accuracy, I can bisect the yellow box. You understood how the method works? So we are able to compute the inverse of a set, and we can do also the sum, Minkowski sum of two sets, or the image of a set, the intersection of sets. We can compute with sets, and in a guaranteed way. It will be used to make proofs later. Okay, I have finished. Normally, yeah. If you have any question.
This CD algorithm was not clear to me. Could you bring it back in?
Yes, yes, yes. It was here, sorry. This one. So the idea is first, I start with a huge box. X0. Okay. I take this box. I'm here. I compute the image by the inclusion function. I decide if I am inside Y, it's not the case. Outside Y, it's not the case. Not the case, not the case. Small, no, it's not the case, still big. I bisect in two.
Just a random or
No, when I bisect a box, is with respect to the largest width, largest length. Okay, so if it is like this, I will bisect like this. I bisect it, and now I have two boxes. So I store the two boxes in a list. So after I have plenty of boxes. Then I take one, and I do it again. So after, the box will become small, and one day they will be inside or outside, and I will be able to decide. And since I have convergent inclusion function, at the end, the process will converge. Okay. Yes?
So is Y box as well?
This what?
Y.
Why? This one is a set you want to invert. I just to show how to compute the inverse of a set, but in practice, it will correspond if I have some inequalities. For instance, yes. If I want to solve an inequality of the form f of x negative, y corresponds to minus infinity 0. If I want to solve an equation, f of x equals 0, y corresponds to 0. Okay. If I have some measurements, most of the time, the set, if I have two measurements, so for instance, it will correspond to one measurement, another measurement, y may correspond to a box. Okay. Yes?
so typically the set that you want to invert is your safe zone, and then
I will see later.
okay.
But normally it corresponds to data or things you know. As soon as if you know, for instance, that the robot is inside the circle, if you have, you know that the robot is at a distance to 10 meters between 10 to 11 of a mark, which is here. So it means that you know that your robot is here. You will describe by x1 square plus x2 square belongs to 10, 11. This corresponds to y. This corresponds to f of x. An information can be represented as a set inversion problem.
But your goal is to control the robot to stay in that.
Later. First, you need to know where you are. And once you and when you want to prove properties on a system, you will have to check that a set of nonlinear inequalities, or a set inversion, are never satisfied. So this problem will never happen, and you can transform it as the inverse of a set is empty. The inverse of what you don't want never happen. Okay.
One
Yeah.
question. What assumption did you make on f? Just continuity or?
Given by a finite algorithm,
Ah, okay.
a computable function. Okay, that's all. Thank you. I think time is over. Yeah, okay. Thank you.